Alright, so today we're going to be going over systems of linear inequalities in two variables. And what makes this a little bit different is that we're talking about systems of linear inequality. So we were doing a situation where we only have one linear inequality, where we would graph the respective line and then we would shade in one half of our XY plane, and then every single area that is shaded, including up into the line and on the line, represented a solution set to the linear inequality. But now we're going to do systems of linear inequalities, where we're going to be dealing with multiple linear inequalities, and then what is the solution set to multiple linear inequalities. So if we graphed one line and shaded in the respective inequality, and we can graph another line and shade in its respective linear inequality, we start to see like, hey, there are some areas where the two shaded regions overlap, and then as that overlapped region, that represents the solution set to the system of linear inequality. And we're going to be interested in this region here representing the solution set to the system of linear inequality. And just to note, we're also going to be interested in this point right here. That might be what I would call like an extreme point or a corner solution to our solution set that might be of interest to us. Alright, so let's do an example. Let's suppose that we have a system of linear inequality, two equations. So we have 2x minus y is greater than or equal to 0. And we also have the equation x plus y is greater than or equal to 6. So we're going to want to graph the solution set to the system of linear inequalities. So let's deal with this equation first. So it might be easier to think about this one and writing it in like y-intercept form, slope-intercept form, I mean. So instead of having 2x minus y greater than or equal to 0, we're going to solve for y. So we're going to get y is less than or equal to 2x. So we're going to want to graph that with a y-intercept of 0 and a slope of positive 2. And what's kind of nice about when we write our linear inequality as slope-intercept form is that we can just look at the respective inequality, and because it's less than or equal to, we know that we're going to want to graph the lower half of the function. It's a little intuitive that way. So if it's greater than or equal to, we graph the top half. If it's less than or equal to, we graph the bottom half. We shade it in the bottom half, I should say. So let's deal with the other linear inequality. So we got x plus y is greater than or equal to 6. Which this might be quick to graph because we can know that when x equals 0, our y-intercept is going to be 6, and we know y is greater than or equal to 6, so we can go up 6 units, 1, 2, 3, 4, 5, 6, do a full circle, and we know y is greater than or equal to 6. And then when y equals 0, then we know that x is greater than or equal to 6. So 1, 2, 3, 4, 5, 6, that is our x-intercept, and x is greater than or equal to 6. We're going to draw a solid line through both our points. Let's imagine that's a straight line for my sake. And then we're going to shade in the respective area that we do have. Alright, so now that we have graphed of both linear inequalities, we can then look where these two functions intersect, or where the linear inequalities intersect. What are the areas where it is doubly shaded? And we can see that we got this like growing triangle shaped out here. That is our solution set to the system of linear inequalities. And we're going to be interested like, hey, what's this intersection point right here? What is this corner solution? So the x and y values that solve for that intersection to an inequality. So we want to deal with the equation. We have y is equal to 2x, and we also have the equation x plus y equals 6. Now notice that these are not inequalities, and that is because we're dealing with the specific lines that we have graphed. So if y equals 2x, we can plug in that 2x for this y in the other equation to solve for our x variable. So we're going to get x plus 2x equals 6, 3x equals 6, x equals 2. And then if y equals 2x, then we know that y equals to 2 times 2, or y equals 4. So we know that the values for this point right here that represents the corner solution is the point 2, 4. All right, so that would be representing some of the most important information with dealing with that system of linear inequalities. We graphed each inequality by itself. We looked at where the two functions overlap or where their inequalities overlap, and that's going to represent the solution set to the system of linear inequalities. All right, let's do maybe more of an economic example, where if we have our demand equation is represented by P equals to 20 minus 2Q, and we have a supply equation represented by P equals to 2 plus Q. And then, so that is the equation that represents the demand equation and the supply equation. And we're going to be interested in shading in the area above the supply curve. Should put maybe curve in parentheses because we're not, the line is actually not a curve, but we just like to call it the supply curve. And below the demand curve. And this shaded in area that's above the supply curve and below the demand curve is an idea in economics called total surplus. This is representing the total gains in trade that occur in the marketplace due to trading being allowed to happen. All right, so once again, we're going to be interested in graphing this system of linear inequalities. So we have two equations. The demand curve is 20 minus 2Q. So we have a y-intercept of 20. Let's do that in blue. And then we have a slope of -2. So that is our demand curve. And we're going to want to shade in the area below the demand curve. Now notice we're only interested in the solution areas that is in the first quadrant of our PQ axis, because you can never sell negative quantities amount, and we never are selling things for a negative price, so we're only interested in positive Q and positive P value. All right, so we can graph the supply equation, P equals 2 plus Q. So we have a y-intercept of +2, and we have our supply, that's our demand. And we might be interested in denoting that, hey, this is the point 0, 2. This is the point 0, 20. And we're going to want to shade in the area above our supply curve. And then we're going to be interested in the area, this triangle here that represents the overlap of both of our shaded regions, and that's going to be representing total surplus. Now, granted, there is one last point that we're going to be interested in solving for, and that is that equilibrium point right here, and that is where the intersection to the lines P equals 20 minus 2Q and intersection with P equals 2 plus Q. So if P equals this and P equals that, we can just set this to equal that. So 20 minus 2Q equals to 2 plus Q. We want to solve for Q. So 18 equals 3q, or 6 equals 2q. So q equals to 6. We're going to then plug that back into one of these two equations to solve for the p-value. This one looks like it's a little bit easier to solve. So at q equals 6, we know that p equals 2 plus 6, or p equals to 8. So that we know that the intersection of our supply and demand equation is the point 6, 8. So look at that. We now know that this total shaded in area right here, this triangle that we have area here, is representing the total surplus in the marketplace to trading occurring. And we have also figured out all the corner points to our triangle here. We got the corner point 0.20, the corner point 0.2, and the corner point 6.8. Those are going to be points that are going to be of interest to us later on. Alright, so that does it for today's lesson.